This part of the lesson will deal with how the aeroplane's takeoff distance is actually calculated. All aeroplanes will have either a pilot operating handbook or an aeroplane flight manual. The purpose of these manuals is to show not only how to operate the aeroplane, but also to detail the aeroplane's performance. Shown on screen is an example of the takeoff performance information. This may be either in graphical or tabular format as shown. For the ATPL performance examination, most of the performance data is in graphical form, and therefore the majority of the lessons will present performance data in a graphical format. The example graph we will use is figure 2.1 on page 3 of section 2 in CAP 698. Firstly, the title of the graph indicates that the graph is for calculating the takeoff with no flaps selected. For other flap settings, you may have to consult another graph. Next, take a look at the associated conditions, paying particular notice to the power and flap settings as shown here. Also notice that this graph assumes a runway that is paved, level, and dry. If the runway conditions required for a given calculation are different, then corrections will need to be made to the values this graph will give. We briefly saw these correction factors earlier. Notice this box here, which highlights the rotation and screen speeds for different weights. A pilot must adhere to these accurately because they are the speeds which have been used to construct this graph. If a pilot were to deviate from these speeds, the required aircraft performance would not be achieved. Having looked at the various bits of information around the graph, let's now examine the graph itself. The left-hand carpet of the graph involves the variations of temperature and pressure altitude. This part of the graph accounts for the effect of air density on the takeoff distance. In the example, we will assume a temperature of 15 degrees at an airfield which is situated at a pressure altitude of 4,000 feet. To use the graph then, move upwards from 15 degrees until you have reached the 4,000 foot pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass. In our example, let's assume a mass of 3,400 pounds. From the reference line, we must move down along the sloping guidelines until we reach 3,400 pounds as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognize that the 150% tailwind and 50% headwind rules that you learnt about in the General Principles for Takeoff lesson have already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more, up to the last reference line. Remember that the takeoff is not complete until the aeroplane has reached the 50-foot screen height. So from this point on the graph, we must move up the guidelines to the end. Notice that some of the guidelines, such as these, have a divergent or convergent nature. Ensure the line you draw reflects this, so try not to parallel your line to the nearest guideline in such a case. The takeoff distance in our example is approximately 2,300 feet from brake release to the 50-foot screen. However, let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the takeoff distance. Since the graph assumes a paved, dry runway, we will have to make corrections to the takeoff distance for these different conditions. You may recall that wet grass increases the takeoff distance by 30% or by a factor of 1.3. Our calculated takeoff distance was 2,300 feet, but correcting it for wet grass would now make the takeoff distance 2,990 feet. Let us now assume that the runway has an upslope of 1%. Again, you may recall that this would increase the takeoff distance by 5%, or by a factor of 1.05. This now makes the total gross takeoff distance 3,140 feet. To comply with the regulations, you may recall that the takeoff distance must be compared to the available distances at the airfield to ensure it does not exceed the limits laid down by the authorities. To remind you of these regulations, turn to page 1, section 2 in CAP 698. The remaining pages in the takeoff section of CAP 698 are the graphs themselves and various examples on how to calculate the takeoff distance or maximum permissible mass for takeoff. On page 2, section 2, is an example you may follow to calculate the takeoff distance. Page 3 of section 2 is the takeoff distance graph, without flap, which we have already used and worked through. Page 4 of section 2 works through an example where, given various field lengths, you can determine the maximum permissible mass you're allowed to carry and still meet the regulatory requirements. Lastly, on page 5 is another takeoff distance graph, but this time assuming that flaps have been selected to the approach setting. Use this graph in an identical way to the one we have already been through. You will need to practice using all the graphs, so ensure you work through the examples in CAP 698 and those in the questions for each lesson. Doing this will help you improve your accuracy in the use of the graphs and help to consolidate your knowledge of the principles you have learned so far. The last part of the lesson will focus on some of the certification specifications for single-engine Class B aeroplanes. These can be found in the document from EASA called CS23. There are only two main specifications that apply to the takeoff phase of flight, and these specifications concern the takeoff speeds. The first of these certification specifications concerns VR. You may recall that VR is the speed at which the pilot makes a control input with the intention of getting the aeroplane out of contact with the runway. The certification specifications state that for the single-engine aeroplane, the speed VR must not be less than VS1. VS1 being the stall speed or the minimum steady flight speed of the aeroplane obtained in a specified configuration. The configuration concerned here is that configuration used for takeoff. The second of the certification specifications concerns the speed of the aeroplane at the screen height. The specifications state that the speed at 15 meters, or 50 feet above the takeoff surface, must be more than the higher of a speed that is safe under all reasonably expected conditions, or 1.2 VS1. You will recall from an earlier lesson that the speed that must be obtained at the screen height is commonly referred to as the takeoff safety speed. The certification regulations about VR and the takeoff safety speed are not found in CAP 698 and therefore must be committed to memory. This completes the lesson on takeoff for the Class B single-engine aeroplane. Familiarize yourself with the format for the aircraft you are flying and correctly adjust the calculated takeoff distance for any variable that is not accounted for in the data. An understanding of the effects of various conditions and factors that control the takeoff will better equip you to ensure that each and every takeoff is well within the limits of the runway available, and thus minimize any chance of an accident occurring. Lastly, do not forget to check the regulation requirements for the takeoff distance.